We are finishing parametrics. The basics anyway. Parametric, let's write that. Equations. Normally, this would be a one-day deal. But most normally you get this in pre-calc too, so we're taking 2 days. Not a big deal. Let's talk about parametrizing the circle.
Tom Smith, family checkout, please.
Yep. Is that a bit early? Thought it was supposed to be 11:30. 11:30? 10:30, 9:30, whatever. Thought it was at the 30.
They said that they might change it.
Oh. Thanks for that. Okay, here are the general set of equations for parametrizing a circle. Okay, R is the radius, and AB is your center. Okay. So it's pretty straightforward to graph these. It's my favorite word now, straightforward. The R's will match. Okay, they have to for it to be a circle. If they don't match, you probably have yourself an ellipse. Okay, because it stretches it one way or another, right? X or Y. So let's just graph. Yeah, you can rewrite it either way. We're going to graph that circle. What's the radius? And what's the center? There you go. That is your circle. Center 0, 0, radius 4. Okay. There is an ellipse example in your book. I'm not going to touch on it. It's very similar here to the circle. The A and the B's change. Smith stole my thunder yesterday, so we'll skip example 6. We've already touched on it. Do you need me to graph any others, or do you think you can handle those pretty easily? You basically choose your t-values, plug them in, graph it, right? They do get kind of funky, some of them. Okay, you can do a lot with parametric curves. Example 7 in the book, the curve actually ends up looking like that. Okay, this is, I think that the graph is something like that. It's t squared plus 1 and t cubed minus 4t. Okay, so no longer are we linear in the x term. Okay, so it creates some nice designs. We'll actually go make flowers and stuff with polar curves. Oh, yeah. Pretty flowers. Okay. I'm going to show you something called the cycloid. The cycloid is a very popular parametric shape. It is formed
If the cycloid is formed by rotating a circle and tracing one point on the outer edge. So this cycloid is started at 0, 0. That point is going to rotate around, and where that point is located traces out the graph. Okay, so and then it comes down and it comes back up, down, up. Okay, this is basically the path that a car tire would trace if you're traveling down the highway. Okay, it's called a cycloid. What do you think the red arrow indicates? That's half of it. It's changing size. Yeah, it's a velocity vector, in fact. So it has direction and it has magnitude. So the longer the red arrow, the faster that point is traveling. Okay. So you can see it actually goes to, how fast is it traveling? 0, right? And then it comes back up, positives, etc. So that's the cycloid. It's a very popular graph to use in parametrics. Okay.
Anybody want to find the area under that curve? No, I'm just kidding. You don't need to. But the cycloid, you can parametrize it, obviously, with those components. Oh, hold on. I mixed those backwards. It needs to be switched. That would have been a circle. So that would be one example. Okay, this is radius 1 and this should be that should be. So this would be one example where the radius is 1. Okay, the radius is not 1 on this example. So generally, the x is RT minus R sine t. And the y is R minus R cosine t. So you have your radius here. That would be how big the arc actually would be. Right? In this case, it's 1. So it's a cycloid. It's just an E shape. Where with parametric curve. So I just want to show you that because it might pop up. Just want you to be kind of ready for it. Sometimes it shows up on the email. So there's kind of a way to graph it. The one that. Okay, good enough. We can do it there. Let's go to derivatives. Okay, slope of the tangent line. Why do we do this in calculus? Because we can find slopes of tangent lines and areas under curves, right? Slope of a tangent line. Remember that's slope of the tangent line, correct? How would I get dy dx out of something that has t's in it? gonna do a little fraction math. You have an x and a y, right? Both in terms of t. Take the derivative of the y and the derivative of the x. Divide them, you have your slope. So, you can also write it like this, if you wish. The derivative of the x and the derivative of the y. Right, so let's look at this function. It's the same one that I showed you, that funky little ribbon graph. That's the one we're going to look at. So t squared plus 1 and t cubed minus 4. What is the equation of the tangent line? T equals 3. What do we need? Point and a slope, right? Same as always. Okay, what's the point?
Y plus t. So y equals 3 and always.
T is 3. So plug T.
Yeah, the y, which is 3. So that would be 9 minus 12 negative.
This is 27 minus 12.
Um,
Yep. Which is 15, right? And this is 10. Okay, there's our point. Our slope, we're still in the xy plane. It has to be in terms of dy dx. Is the derivative of the y. So what's that derivative? 3t squared minus 4, right? It's in terms of t. And the derivative of the x is 2t. And then we evaluated at t equals 3. And we get 23 over 12. Okay. 6. Can we multiply properly? There's your slope and your point. You can write the equation. Good to go there. Nice. Nothing you have to see, you just need to apply that to parametrics. What about horizontal tangents? Where are horizontal tangents? Yep. Okay, so you're thinking this is kind of the same as implicit differentiation. You want the derivative to equal 0, correct? Well, does the bottom matter at that point? No, so just the top. Okay, so 3t squared minus 4 equals 0. And that's just the y derivative. So do your math. So are those the points where the table is sit? It's just the t values, right? You actually have to go back and plug your t's in here to get your points. Okay, so think about we're looking at the graph. I'm going to show this back up here. Wow. Right. That's these spots right here. So, do you want me to put those back in and give you the numbers, or are you good with that? So you look confused. That's a t value of positive 4/3, square root of 4/3. You got to plug it in. Both these to get your xy coordinates. So positive 4/3 gives us. Okay, what's 4/3 plus 1? 7/3. And then, is that good? 4/3 to the 3/2. Minus 4. Good enough. So that would be use the root of 4/3. You would also have 1 for t equals negative root of 4/3. Good to go? You can handle those, calculating slopes and horizontal tangents and all that stuff. Okay, fine. Be that way. Non-responsive, a bunch of dead people. The Walking Dead. There is another example called the Bezier curve. In your book, if you want to look at example 10, I'm not going to show it to you because it's not really that big of a deal. So those are the basics of parametrics. How to graph them, how to change from XY to parametric form, and then how to calculate a slope. Okay. Tomorrow, we look at more parametrics, but we are doing arc length and speed. Okay, because the component of time, and your arc length and speed calculations are going to be pretty similar to what you already know. But just another formula, no big deal. Okay, you want me to write these items back up? Good, I got it. Got it? If you need it, it's on that paper. Thanks for listening. The rest of the hour is yours.
All this class is anymore, isn't it? One more formula every time.
Pretty much.
It's always one more formula.